We're going to start with our overdamped response type, which has a total response as shown here. So remember, this overdamped response is one that was kind of the slow but steady. It eventually gets there. It takes a little longer, but it's not going to overshoot. So let's look at an example transfer function that would have an overdamped response. So g of s equals to 9 divided by s squared plus 9s plus 9. So this is in that general form we had with our b divided by s squared plus as plus b. In this case, a and b are both equal to 9. So we can factor out those two poles in the denominator, and we get that this is 9 divided by s plus 1.146 times s plus 7.854. And so we see we have two real poles. And so that's going to be true for our overdamped response. So we have two real poles. And so what we're going to see is that we can tell what response type we're going to have just by looking at where our poles are. So that's going to be very useful to do. So again, you might see this presented in the S-plane as opposed to in a transfer function equation. So in our S-plane, we have our real axis, our sigma, and our j omega, which is our imaginary axis. So in this case, we have approximately negative 1.1 and not quite to scale, but here's approximately negative 7.9. So we would have a pole at each of those two locations. And in this case, no zeros for this transfer function. So it turns out above we plotted our our total response is shown here. Our natural response for an overdamped system is going to have the following form. So natural response has the form of c of t is equal to some constant k1 e to the minus sigma 1 t plus some other constant k2 times e to the minus sigma 2 times t. And so with this natural response, the sigma 1 and sigma 2 are the pole locations. So that's going to dictate how quickly those decaying exponentials go away. And then as we saw with our general first order system, our k1 and k2 constants are going to depend on the input function as well as the specific pole location of our transfer function.